Good morning, everyone, and welcome to the fourth lecture in category theory. In this lecture, we are going to look at one of the most important concepts of category theory. But I just realized that I need to connect my pen. Sorry about that. Okay, let me start again so I can cut the beginning out from the video, which is easier than cutting the middle part out. Good morning, everyone. This is the fourth lecture in category theory. We're going to look at one of the most important concepts of category theory, at the same time one of the most difficult ones, I guess, when you begin learning the subject. And in some sense, if you want to tell the difference between a novice in category theory and someone who actually understands the subject, it can be judged whether this person understands the concept we're going to discuss today or not. So if you will have a good understanding of the concept by the end of the lecture, or maybe a few days after, then you can consider yourself to be on the expert side. Okay, so the concept is that of an adjunction. But before we jump into giving the definition for what this is, we're going to provide a careful motivation for the concept, since the intuition behind the concept, in some sense, is the key to understanding the technicalities that come after. In a world where mathematical structures are just extremely discrete entities, sets. In a world like that, we have this idea of a one-to-one correspondence, where we go from one set X, let's say, and at the other set be Y. We go from X to Y by mapping elements in such a way that it is possible to reverse the process. So what do I mean by reversing the process? Well, there is a mapping backwards. And the feature of this mapping backwards is that if you go forward and then backward, you will end up at the same spot. And this is true irrespective of whether you start from X or you start from Y. Here is a comprehensive picture of a one-to-one correspondence, or in other words, a bijection. And this is the best we can do when our mathematical structures are just sets. Why is it the best thing we can do? Well, what else could we do to say that two structures are kind of same or similar? If I had a feature that allowed me to maybe compare elements of the set with each other, then maybe I could have required that if I go forward and then I come backwards, I don't get exactly the same thing that I started with, but I get something that's approximately the same, or maybe there is some comparison from one to the other that's good enough to kind of claim that this is not quite the same as the starting point, but it's not too far from it. But that I could do if I had a way to compare elements of the set. But I don't have a way to compare elements of the set, so I need to require that on the nose we have this property that going forward and backward gives me exactly the starting point. But in a category, we have a way of comparing objects, and these are called morphisms, right? So let's see how we could relax the notion of a bijection if we are working instead of sets, if we're working with categories. So I'm going to then draw another picture. a bigger one, where now these two entities are categories. So let's call this C and D. And we have a functor running in both directions, so a functor F, and we have a functor going backwards, a functor G. And when I start with some object, maybe I'll call that object C. When I start with C, I apply the functor. It gives me object f of C. And then I apply the functor backwards. It gives me the object g of f of C. And g of f of C might not be equal to C, but let's say that we've got a morphism going from C to g of f of C. And let's call this morphism eta with a subscript C. Of course, now that we already know what a natural transformation is, we probably want to require that this family of morphisms, one for each C, is a natural transformation. So we will call the entire family, we will call eta, and let's require that eta is a natural transformation from the identity functor. I think from the previous lecture we can identify that the domain of eta will be identity functor. We already considered such natural transformations in the previous lecture. It's the identity functor of C. That's a functor that maps every object to itself and every morphism to itself. And the codomain of the transformation is the composite functor GF. Okay, so all good so far. But now what about the other side? We might want to have something similar on the other side. So let's say if I now started with an object D, and I first travel this way to get me to something I'm going to call G of D, because it's the functor G applied to D. And then I return with the functor F, I return back here. And this will give me F of D of G of D. And I might want to require that I've got something similar here. But now I want to decide the direction of this arrow. Should the arrow be directed this way? Or should the arrow be directed that way? If we follow this principle on the left side, then it seems like the arrow should be directed that way. But on the other hand, if we allow the arrow to be directed that way, then we can get something very interesting by combining these arrows with each other. And let me show you what I mean by that. So we could have taken now this epsilon, which is another natural transformation. So let's write this out first. So epsilon we might want to require to be a natural transformation from the composite FG to the identity of D. And if it happens so that the morphism D, sorry, not the morphism, the object D is the same as the object F of C. So let's try to look at this morphism in a case when our starting point D is actually an object coming from the other side. And let's see what happens. So I'm going to illustrate on a separate diagram. This is just to explain why I want the direction of the epsilon morphism be the way I drew there, instead of it having the other direction which match more with what happens on the side of the category C. So now I start with an object C. I apply f of f to that object. I get f of C. Then I apply G to that. This brings me to G of f of C. And then I apply f one more time. If I apply f one more time, I'm going to land at f of G of f of C. And remember, the epsilon morphism is directed into my starting point on the side of the D category. So here on the side of the D category, my starting point was f of C. So I took the case when D is equal to f of C. So the arrow will be directed this way. Okay, so let's continue going back and forth. Let's now apply G one more time. So we now take this object here and we map it again by G. We will get something long. We will get G of f of G of f of C. Okay. Let's insert some of the arrows we have here. So I've got this arrow eta of C, right? And then what else do I have? There is something strange here. Okay, so any ideas? What else can I draw in? Is there any other arrows I can draw in? I want to somehow, what I'm trying to do here is to have some kind of relationship between eta and epsilon, but they live in two different categories. So I struggle to have a relationship between them if they live in two different categories. But maybe by going with the functors back and forth, I can kind of bring some versions of them at least together and then try to compare them.
Sorry, Prof, shouldn't it be epsilon sub f of C?
Yes, it should be. Thank you. This is epsilon of D, which is the same as epsilon of f of C. What can we draw here? What else can we insert in this picture? So remember, we have two functors, one f going from left to right, and the other one g going from right to left.
If I may take a stab, there is at least one eta going from GFC to GFGFC, right?
There is one, yes, indeed. Let's draw that in. So this is eta of GF of C.
And another one, the epsilon, we can map under G, I'm guessing.
We could. If we map epsilon under G, we're going to get an arrow going from here to there, right? So the domain of epsilon is this, and the codomain of epsilon is that. So if we transport epsilon on the other side, we'll get an arrow going from there to there. So let's draw that in. Maybe I'm going to use a yellow color for this. In a sense, this is an alien coming from the other category. So we've got here epsilon G applied to the functor G applied to epsilon of f of C. So it's interesting that now the eta and the epsilon are kind of facing, kind of going opposite ways. Okay, there was also a note in the chat, which I think is the same as what we wrote here. Let's see what we can draw on the right-hand side as well. We also have, don't we also have f of eta from the left side, on the right-hand side? So we have, maybe I want to choose my colors more carefully now. So let me not use yellow for this because we used yellow for the mappings. Let me rather use this, use the color blue for that. And I'm going to use the color red for whatever comes from left side to right side. So we've got this one that was G of epsilon of f of C. And then on the right side, I also have an arrow going that goes this way, right? And that's f of eta of C, isn't it? Okay, so we now suddenly have arrows that kind of go in opposite directions. And when we have arrows going in opposite directions, and when these arrows are between sets, we want them to be inverses of each other, right? Here we were exploring a concept where we have arrows going in opposite directions between categories, so these arrows are functors, but we don't want to force them to be inverses on the nose, right? We want to relax the idea of inverse a little bit, and with the thought of relaxing the idea of inverse a little bit, we introduced this idea of kind of approximation that going forward and backward lands me in some approximate version of my starting point. And so now I have further arrows, the ones that live inside the category, and now I discovered that these arrows are going in opposite directions. And maybe at that level, I want these arrows to be inverses of each other on the nose. For example, if I start with object C. And then I go there and come back. And so this GF of C is kind of approximation of C. Now, by applying the functor f to this thing, applying the functor f to this arrow, will give me a corresponding approximation of f of C being approximated with that object f, g, f of C, right? But at the same time, I have another approximation on the right side, the one that goes the other way around. And so maybe I want these two approximations to be reversible processes. So what I'm going to do, I'm going to require that f of eta C, if I go from D to that object FGF of C and then come back, by epsilon of FC. If I compose these, I'm going to require that that composite must be the identity morphism of f of C. Do I want to require also the other way around, that if I swap these around, then that is also an identity morphism? Maybe not. But at this point now, what I'm saying is becoming a little bit suspicious. Why do I make some random choices of what I require? So I guess I'm not succeeding in motivating this well. But in the notion of adjunction, this will be required, and there will be another identity required that is similar to this, but on the other side. And that is where we begin. So it's a kind of opposite picture to this, where we begin with not eta C, but we begin with epsilon D, or an abstract D. So let's write that down. So let's try to copy this picture, but with now the roles of the categories C and D swapped around. Okay. So I'm going to start with an object D. Then I'm going to map it by the functor G. I'm going to get G of D. Then I'm going to map it forward by the functor F. I'm going to get F of G of D. And here I have my epsilon of D. And then I'm going to map that epsilon of D by the functor, which will give me a morphism from from G of F of G of D to G of D. And so I should draw that morphism with the blue color. So this is G of epsilon of D. And I also have a morphism going this way, which is my eta of G of D. Why do I have a morphism going that way? Well, remember, if I think of this as my object C, so if this is my object C, then this is just the epsilon, the eta of C. And so I have again a situation of two arrows going opposite ways. And just like here, I'm going to require that they compose to identity at the more simple object, which is G of D. So if I go back here, I require that if I go up and then down, right, it gives me identity. So it gives me identity at the object f of C. In a sense, you can think of it like this. We require this to be identity at f of C because f of C is like less distorted object. If the functor was only applied once to C to get f of C. Here we have much more distortion. So maybe hoping that that way we also get identity, maybe that's too much. And so writing this down, we'll get that G of epsilon of D composed with eta of G of D must equal to the identity of G of D. So in the end, we have two equations. And these two equations are going to define what is called an adjunction. So let me now formulate a definition. I will come back to motivation and also examples. An adjunction is a four-tuple consisting of two categories C and D. Well, actually not four-tuple, but six-tuple. So let me just call it tuple. Consisting of two categories C and D, two functors F and G, and two natural transformations eta and epsilon, where C and D are categories, F is a functor from C to D, and G is a functor from D to C. And eta is a natural transformation from identity of C to the composite GF, and epsilon is a natural transformation from the composite FG to the identity of D. So these are natural transformations. Such that we have these two identities. This one. So this should hold for all objects C in the category C, and the other one. And that one must hold for all objects D in the category D. So we kind of came up with this notion. At the moment, it's a very experimental thing. I mean, we don't even know if this makes sense or not. We have no idea whether we'll have good examples of this or not. We seem to have made a little bit random choices here in terms of what identities to require. But at least we have some starting point. And now the next step for us would be to go back to the original problem of wanting to have a one-to-one correspondence between categories, which is a bit in a relaxed sense than the usual one-to-one correspondence. So go back to that problem and try to look at an example where a need would arise for having a more relaxed correspondence between two categories. So let's choose then an example that would be closest to what we already know well in mathematics. And I think, at least in South Africa, but I think this is applicable internationally as well, one of the mathematical structures that are studied well at undergraduate years are vector spaces. So let's see what we can do by trying to compare the category of sets with the category of vector spaces. And let's, for simplicity's sake, take vector spaces over real numbers. Okay, first of all, do we have one-to-one correspondence between these categories? Are there functors F and G such that, because if we have a one-to-one correspondence between these functors, the genuine one, so having functors F and G such that G composed with F equals identity of set, and F composed with G equals identity of vec, if we have such functors, then this will not be a suitable example to motivate a more general notion, right? A more general notion of one-to-one correspondence. Now, as it is usual in mathematics, when you want to prove that two mathematical structures are not isomorphic, one of the standard techniques is to find a property of one structure that does not hold for the other one, because isomorphisms are supposed to preserve properties of the structures. So if you've got a property of one structure that doesn't hold for the other one, then you will know that it's impossible to have an isomorphism between them. Isomorphism is, of course, a general term for having two structure-preserving maps whose composites are identity maps on each side. There is one very beautiful property of the category of vector spaces that does not hold for the category of sets. Maybe there are many others as well, but I think the simplest one is the one I'm going to share with you. But to share that, I first need to define a concept, and let me quickly check if we've already defined that in the first lecture. This would be the concept of an initial object or a terminal object. I don't think we've defined it yet. But let me, instead of defining new concepts, let me actually try to make use of the concepts we did define in the first lecture. We defined the concepts of monomorphism and split monomorphism there. And then we remarked this interesting phenomenon that, so let me just quickly remind you what these were. So a monomorphism from object X to Y was a morphism M such that whenever you've got two other morphisms, W1 and W2, if M composed with W1 equals M composed with W2, then this implies that W1 equals W2, and this must be true for all W1 and W2. Whereas, so that was the notion of a monomorphism, and the notion of a split monomorphism was that I have a one-sided inverse, so M is a split monomorphism when there is a morphism backwards. Let's call this M prime, such that M prime composed with M equals identity of X. And we made the following observation, that in the category of sets, every monomorphism is a split monomorphism except one type of monomorphisms, except the empty functions. So the functions that go from empty set to some other set Y. These functions are not split monomorphisms simply because there's no way to go back. From a non-empty set Y, we will not have a function to the empty set. Of course, if Y is empty, then we still have. But what about vector spaces? Is it true that every monomorphism in the category of vector spaces is a split monomorphism? Okay, so before we go to monomorphisms, let's describe what they are. I mean, before we go to the category of vector spaces, let's describe what monomorphisms are in the category of sets. In the category of sets, these are injective functions. And it turns out that in the category of vector spaces, this is something we are not going to prove now, but it's not difficult to prove at all. Monomorphisms are injective linear maps. So these will be injective linear maps. And because empty space does not exist, a space needs to have at least a zero vector, the problem of having a splitting disappears. And every monomorphism is indeed a split monomorphism. So just an example to illustrate this idea. So let's say we take the one-dimensional vector space. We have a mapping here that maps every point to the x-axis. And so that gives us a certain monomorphism M. But now how do I go back? I can go back by the projection function, right? So pi of xy equals x. And in a general situation, if you've got an injective linear map, it will map your basis vectors of your domain into some linearly independent vectors in the codomain, and then you complete that to a basis, and whatever vectors didn't come from your linear map, you can map them back any way you like, and then you get a function from the basis of the codomain to the original vector space, and that function determines a linear map, because a linear map is always determined by where we map the basis vectors, right? And that function will turn out to be one-sided inverse of the injective linear map you started with. Now, both of these notions, as you see, are expressed in the language of objects, morphisms, and composition. And it's not difficult to prove that if you've got an isomorphism of categories, which is what this would have been, so functors going back and forth, so that their composites are identity morphisms, identity functors on each side, then whatever is a monomorphism here would be exactly what is a monomorphism on the right side. So all monomorphisms will map to monomorphisms. All split monomorphisms will map to split monomorphisms. Moreover, if something maps to a monomorphism, then that thing on this side must be a monomorphism. And so the property of being monomorphism and split monomorphism is both preserved and reflected by the functors. Which means that if on this side, monomorphisms are not quite the same as split monomorphisms, they can't be the same on that side either. But on that side, they are. And so isomorphism between these two categories does not exist. Okay, so isomorphism does not exist, and therefore we are exactly in a situation where we want to maybe relax the idea of isomorphism to get perhaps an adjunction in the way we defined before. So let's begin with the set X, but now we have to be a little bit creative here. If we begin with the set X, I would want to choose some functor F, and maybe we'll choose the most natural one, and just to give you a hint what the functor will be, when we call it set B. So we'll take the vector space whose basis vectors come from the set B. Nick, is there standard notation for this in functional analysis?
Is there a standard notation for constructing the free vector space with basis B?
Yeah.
I'm going to say no.
So let's just call it FB. It's a vector space. Well, I mean, we could have yeah, unfortunately, when B is infinite, this notation is no longer good. Yeah, but otherwise, if B was finite, we could have denoted it by B power of R. Because when B is finite, the space of all functions from B to R is the space we're looking for. But when B is infinite, we only want those functions that have finitely many non-zero values. So there's no notation for such function space.
None that I'm aware of. There might be, but I'm speaking under correction. I'm not aware of a standard notation for what we're looking for.
So it's the vector. We can think of this as the vector space. Okay, maybe let's keep it simple. And the vectors, it's a vector space with basis B.
We would write something like the space of all finitely supported functions on real-valued functions on B or something like that.
Right. Okay. So that's our functor going from the category of sets to the category of vector spaces. How is it a functor if I have another set B prime? Then I could get and if I have a function between them, I could get a linear map that's defined the following way. So f functor applied to the function f. So because B is a basis here, every vector in here can be expressed as a linear combination of basis vectors. So I consider that decomposition. And then I apply f to each basis vector and consider then the corresponding linear combination in the other vector space. I think we've already considered this functor before. So we get functor one way, going from the category of sets to the category of vector spaces. And this seems to be like the most natural way of creating a vector space out of a set. What about a functor backwards? If I have a general vector space V, what is the most natural way of creating a set? Well, there are two ideas that come to mind, right? One is to simply consider a basis of V. There is a problem with that idea, though, because if I take the basis of V and I have another vector space W and I consider the basis of W, what if I now have a linear map between them that does not map basis vectors to basis vectors? So considering the basis of V does not give me a functor. Too bad, then we have to stick to the other option, where we simply assign to a vector space its underlying set of all vectors, not just the basis vectors. So that will be our functor G. So G will map a vector space V to the same set V. So before V was a vector space, but now it's just a set. So this is on the right side, it denotes a vector space. On the left side, it's just the set of vectors. So we remove all the structure from a vector space. Okay, now let's see if we can, well, I'm not describing how this is defined on morphisms. That will be trivial. A linear map between vector spaces, of course, will give me a function between corresponding sets of vectors. Now let's see if we can isolate this idea of approximating my starting point with two natural transformations, eta and epsilon. So before even deciding the natural transformations, maybe we should first see if we can find the arrows. So I begin with a set B. I construct this vector space whose basis is B, and then I map it back. And so this is what I call G of V, right? So G of f of B, which as a set actually equals f of B. Will I have a natural function from B to G of f of B? And here I would like to get some suggestions from you. How shall we define eta B? So we can think of this as all possible formal linear combinations of vectors in B, of elements of B. And now can I map B into the set of all possible formal linear combinations of elements of B?
It would be a type of inclusion map.
Yeah, so what will be the value of the map at B?
B itself?
Yep, let's try that. Why not?
Okay.
This seems to be a very natural map from the set. So basically from the basis to the vector space of which this thing is a basis. Okay, so it seems like we've got an eta. We still need to check that eta is natural transformation, but let's first try to identify an epsilon, because if we can't identify an epsilon, we don't need to even proceed with this. So let's first identify an epsilon, then we will check that each of them are natural transformations, if they are. So to identify epsilon, I need to first begin with a vector space, then consider the set of vectors, and then map that back to here, which will be now a vector space whose basis is the entire space V. This is going to be a huge vector space, right? Usually vector spaces are infinite, right? Well, real numbers, they are all infinite except the trivial space. So we've got this infinite, possible infinite set here, right? And now we're taking a vector space where we've forgotten that V was a vector space itself. We now treat V as a raw set. And we now are taking all possible formal linear combinations of elements of V. And that's our new vector space. We're not allowed to evaluate that linear combination because remember, it needs to be, I mean, this V needs to be a basis. It cannot have one of its vectors being a combination of the others, then it's not linearly independent anymore. Do I have a map going this way? Do I have an epsilon V here? So to define epsilon V, I will have to state what will be epsilon V of a formal linear combination of vectors from V. And to distinguish formal linear combinations between actual linear combinations inside the vector space V, I'm going to use a notation which I never use otherwise. I'm going to write these arrows there. Maybe this is not the best convention, but so by writing this arrow there, I'm emphasizing that this is not the actual linear combination inside V, but it's a formal linear combination. How can I map a formal linear combination of vectors from V to back to the vector space V? Any ideas?
I could try to take the stab. The V's are all finite linear combinations of the basis.
Okay.
So we can take the coefficients we can take in, and we can rewrite that whole thing as a linear combination. Okay, hang on. We assign a basis to V. We go.
Do we need to? Do we need to assign a basis?
I am now unsure.
maybe there is a simpler way to do the same thing that you want to do. So V1 up to Vn are vectors in the vector space V, right?
Oh, yeah. You just add them all up.
Yeah, we just evaluate the formal combination inside the vector space. So we just remove those vector heads. So we just evaluate this in. Thank you. So we just evaluate this in the vector space. So we take a formal linear combination and we evaluate it. I mean, this idea of evaluating a formal combination should be very familiar to us, right? For example, when we work with polynomials, what is a polynomial? A polynomial is a formal combination, but then you want to substitute values in the place of your x's in the polynomial. That's when you start evaluating, right? So the same here. So we can think of this as a formal combination, but then we might actually want to compute the value of that combination inside the vector space, which we can because vectors v1 to vn come from the vector space V. All right, so we seem to have identified two approximating maps here. One eta and the other epsilon. And what we want to do next is, first of all, to check that they're natural transformations, and then to check that the adjunction laws hold. And then after that, maybe to get convinced that this is really the best we could have done, in the sense that when we were deciding here, if you recall, where are we now? When we were deciding here which composites should be identity, we said, let us assume that we've got identity at the simplest object, maybe not at the more complex one. And then maybe we can check that in this example, indeed, we only have those identities that we did require, and we're not going to have the other ones. That would be a better motivation of why we made that choice then. Okay, so we're going to first, as I said, check that these are natural transformations. So let's do this slowly and step by step. So let's first check that eta is a natural transformation. You see, in fact, while I'm making my screen bigger, let me make a general remark that linear algebra, specifically understanding of vector spaces and the whole theory that goes around it, is a very, very good platform for understanding concepts of category theory. So that basically means that one could introduce category theory in a third-year course if the second-year course does a fair treatment of linear algebra. Okay, so I'm going to draw that picture again, one for checking that eta is a natural transformation, the other for the other one. So we want a natural transformation from C to G of f of C. And what does it mean to be a natural transformation? It means that if I have a morphism from C to C prime, let's call it F, then I could have applied my functors back and forth to the morphism F. So on this side, I would have had f of C prime, f of F, and then apply the other functor, which is the G functor. So we get here G of f of C prime. So here we have G of f of F. And then we have another eta there, eta of C prime. And so that's applying the GF functor. And then we also want to apply the identity functor. But if we apply the identity functor to this, we just get back the same thing. And so naturality of eta means that this square commutes. Now, I am relying on the fact that you remember what a natural transformation is from the previous lecture. And if you don't, then just believe me that checking that eta is a natural transformation, we have to check that this square commutes. there's a nice intuition behind this. Basically, we're saying that if we approximate C and then apply the function f, then it should be the same as first applying the function f and then approximating. If eta were to be an identity map, so if we have its one-to-one correspondence business, then GF would want the functor GF also to be identity on f. So if I put equalities here, then the square to commute is the same as just saying that f equals GF of f. So we get back the familiar idea of one-to-one correspondence happening not only at the level of objects, but also at the level of morphisms. Okay, but we now need to interpret this in our specific scenario where our C is a set, and specifically we've now called it B. So we've got some set B, and then we have B prime. And here we have GF of B prime, and here we have GF of B. And we should put the B here subscripts of eta as well. And then also we need to remind ourselves what f and gf do. So remember, f is just taking the vector space with basis b, and g is taking the underlying set of vectors. So in fact, gf of b is a set is the same as f of b in this specific situation, and the map eta just maps every basis, every element of b to that vector in the vector space. So I begin with an element of b here. What do I want to check? I want to check that the composite eta b composed with gf of f equals eta b prime composed with f. That's what I want to check. And I will check that by applying both sides of the equality to an element in B, and then computing both sides and seeing that they give me the same result. But I'm going to do it diagrammatically instead of algebraically. So I'm going to draw various arrows showing me where B gets mapped to by each composite, and then I will see that they do match in the end. So by the eta map, B gets mapped to the same B here. Where does B get mapped to here? Remember, what is G of F of F? So it's the linear map that's determined by mapping these basis vectors to those basis vectors by the function F. And of course, that linear map, the linear map F of F, will map B seen as a formal linear combination of itself, where we just see this as 1 times B, right? It should map, by the way f of f is defined, to 1 times f of b. So in other words, it should map to f of b. So b there, by this map, will map to f of b. If at any point I'm a bit too fast and it's not clear what I'm saying, please do interrupt and ask. So that's what happens to b if I go around the diagram this way. Now let's see what happens to b if I go around the diagram this way. B gets mapped to f of b, and then f of b is an element of b prime, and it gets inserted in my vector space just by mapping to itself, right? That's how eta works. Eta maps everything to itself inside this space. So you see, if I apply one composite to b or the other composite, I do end up with the same f of b. So this holds, this equality, proving that eta is a natural transformation. Does anyone want to ask anything? Maybe some part of the argument wasn't clear. So it's a natural transformation from the identity functor of C to G of F, to G composed F, sorry. Okay, so now let's look at the other side. The other side will be a bit more complex, because here the eta map was defined in a very easy way. That's why it was a bit easier. but it won't be too complex either. We take two vector spaces, V, W, and a linear map between them. Let me still call it F. Then we map these by the functor G. I get a function G of F, which is exactly the same function as F, because a linear map between vector spaces is defined as a function between sets of vectors that's linear. It's just a property that distinguishes it from just a function. As a structure, as an object, it's the same object as the F here. As long as I'm thinking of this as the same object as that, which is it isn't. But even when the vector space is a set with extra structure, the definition of a linear map does not need the extra structure as part of its structure. So it's a structurally linear map is just a function from the underlying set of V to the underlying set of W. That's why we can think of G of F being equal to F. And then we apply, we consider this, we build those vector space of formal linear combinations on both sets. And we get our evaluation maps, epsilon V and epsilon W. And on this side, we have the FG of F. And now I need to do the same thing. I want to prove that this square commutes. So I'm going to do that with the same strategy. I'm going to pick an element, but this time maybe I'll do the argument algebraically because we need to compute those formal linear combinations. I'm going to pick an element here. How does an element here look like? We decided to have this notation R1 V1 bar plus all the way up to Rn Vn bar, where by putting bar on V, we are saying that this is not an actual linear combination of the V vectors in the vector space V, but it's a formal linear combination on a vector space where V is just the set of basis vectors. By the way, I just remembered that when we described epsilon, we never checked it's a linear map. We should have checked it's a linear map, but I think it's obvious that it preserves linear combinations because basically it's evident from the way it's defined. Okay, so let's compute now what will be epsilon W applied to FG of F, sorry, composed with FG of F. Or in other words, epsilon W applied to FG of F applied to a formal combination. So what does this map do? The GF map, it just inserts. Remember, this is the vector space where V is a basis, and so the way the linear map corresponding to a function is defined is we just map these vectors to those vectors by the function f, and then a formal linear combination will get mapped accordingly by mapping each vector in the formal combination. So this will result in epsilon W applied to a formal combination of f of V1 bar, f of Vn bar. So why do I not have here f of V1 bar? Because in here, V1 is just an element of GV. It's not V bar that's element of GV, it's V1 that's element of GV. V1 becomes with V1 bar when I want to just have a notation for formal combination to distinguish it from an actual combination in V. But once I map each of the V vectors by the function f, right? And then I want to create the corresponding formal combination here. And when I create a formal combination out of elements of GW, I need to put bars on on the elements of GW to indicate I've got a formal combination. Okay, now let's go back to see how this epsilon is defined. If I go back here, epsilon just removes the vectors, right? Actually, it wasn't bar, it was a vector before, so let's stick with that. It just removes the vector lines. It means that it evaluates the combination. So epsilon of that will simply be R1 times f of v1 plus all the way up to Rn times f of vn, which is now a vector in W. But remember, f was a linear map. So we can factor f out here. We'll get f of R1 v1 plus all the way up to Rn vn. Right? But what is this? Let me show you once again this formula. That is the same as epsilon applied to the formal combination. So we have here f of epsilon v applied to the formal combination R1 v1 bar, not bar, vector v1, sorry, plus all the way to Rn vector vn. What does that mean? That means that this composite equals, I think I made a mistake here. No, I didn't. Sorry, didn't make any mistakes. Equals to f composed with epsilon v, which is exactly what we want in order for epsilon to be natural transformation. We proved that going around this way in the diagram is the same as going around that way. So that diagram commutes. So we've proved that equality, and therefore we can say that epsilon is a natural transformation as well. It will be a natural transformation from Fg to identity functor of D. Okay, now let's go back here and fix some notation. So our C is the category of sets. So let me put set here. And our D is the category of vector spaces. So we put here vec. Great. So we did the first two things we wanted to do, which was to establish that eta and epsilon are actually natural transformations. And now two further things remain, which are these identities. And then we'll get an example of an adjunction. So let's copy these out and then interpret them in our specific scenario. Maybe at this stage, I'm going to write here what we're trying to do. To get an adjunction, it remains to prove, it remains to establish these two identities. Actually, I don't like that line there. Okay, maybe I'll just move this down here a little bit. I think by now we have a good grasp of each of these maps. So let's just do the computation and get it done. Maybe we first just adjust notation slightly so that we are in a more familiar scenario. So f is being applied usually to a set B, we're going to replace C with B here. And G is usually applied to a vector space B. So I'm going to write V in the place of D. And then we will compute each of the left-hand sides here and see that we get identity. So we will apply these composites to actual objects. So just a quick diagram to show what the domain and codomain of these maps are. Well, maybe this kind of indicates already. So for the first identity, we have a map going from FB to FGF of B. This is via the map F of eta B. And then we have epsilon of FB, which takes us back to FB. And I want this composite here to be the identity morphism. So then I'll begin with but remember what is a vector there? It's a formal combination of vectors in B. So I'll begin with R1, B1. Now that I think we don't need to do because let me see. Perhaps our notation was a bit not consistent, or it was maybe consistent. Let me check. Yeah, we never wrote out yeah, we did. So maybe we should have had these vector symbols here as well above the B's, because we are trying to get a formal combination of elements of B. And if we do, then we have to probably put it. No, we probably don't have to do that. Anyway, so if I really want to insist on the notation with this the vector notation for formal combinations, then this was also a formal combination, right? So I should have probably written it this way, but I didn't because we didn't know that B was a space or anything. It was just a set, so there was no danger of confusing a formal combination with another one. But we then insisted on that notation when we knew that our set was itself a space. So let's keep the same style of notation. And so here, when we don't know that B is a space, that we don't need to insist on that notation. So we have a formal combination of elements of a set B. And then we apply to it the functor f applied to eta. But remember what eta does. Eta keeps well, okay, so let's do it slowly. So if I apply this thing to f of eta B, so this is the linear map that is determined by mapping basis vectors by the map eta. But remember that eta maps everything to itself. So we will get R1, B1 plus all the way plus R and Bn. But now, once we apply eta B to each B, this is an element of G f of B, right? But f of B is already a vector space. And so these B1s now seen as, well, eta B is of course the same as B. But now this comes from a vector space. And so here we want to have a formal linear combination because that's what the vectors here are. But now that needs to be distinguished from the actual combinations there. So here I do need to write the bars. And then what epsilon does to this thing is to evaluate it. So I'll get this. And you see we ended up with the same thing we started with. It's an interesting computation because there's nothing complex going on in terms of arithmetic operations of taking linear combinations. It's more about complexity, is more about keeping track of careful track of appropriate notation. So something that we might not be very much used to necessarily when we work with vector spaces in the second year, let's say. So this is the same as the identity map applied to. So because we know f is a, we don't even need to know that f is a functor palette. So this is just the identity linear map, right? So it would therefore RB1 plus all the way up to Rn Bn. If we apply to that the identity linear map, we'll get back the same thing. So that's how we get this equality. And you see we established that this composite equals that, because applying them to every single vector in here results with the same vector. So we get this equals that. Now, what about the other one? What about this identity? But before we go on with this identity, was this computation understandable? Okay, I'm going to assume that the silence means that either it was extremely well understandable or it was absolutely confusing. Maybe in either case, it makes sense to carry out the other computation also and then talk about questions. So this one now corresponds to the diagram where we apply eta to GV. So we go from there to GF GV, and then we apply G of epsilon V to take us to GV, and then we want to have identity here. So we want this composite to be the identity map. The way one usually represents that fact in category theory is to draw a stretched equality there. So one could use the same representation there as well. So the stretched equality represents identity morphism in a suitable direction. So the direction can be kind of guessed from the direction of the other arrows. Okay. This one should be, I think, easy enough to carry out on the diagram. We won't need long computations for this one. So if I pick a vector here, this is sorry, an element there. It's just a vector of the vector space V. Remember that this is just the set of vectors of the space V. And then what does eta do? Eta maps V to the same V, right? But we have to be a bit careful now because this is a vector space, the space V, and this is another one. Fg of V is another vector space. And when we were thinking of vectors of V living inside another space, we inserted this arrow notation to distinguish from the actual vectors of V and the vectors that we build out of V seen as a base. So we actually need to write the line there. But the epsilon map is the one that removes those lines. It evaluates this linear combination, which is just 1 times that inside the space V. So eta inserts the line and the arrow, and epsilon removes it. And so we do end up with identity map V maps to V. So both of these hold, and so we have an adjunction. Now, I do want you please to tell me which parts were not clear. Do not worry that you might interfere with the dynamics of the lecture, because it's more important to understand everything than to move on without understanding things. So we'll first take some questions on what we've been discussing here, and then we're going to move on after that. If you felt like everything was indeed understandable, then if you tell me, that will also be helpful, then I know I can move on.
Prof, it was mostly clear to me. I'm a little bit rusty on vector spaces, so I just need to brush up on a few things before I fully understand. But I have a question around whether the eta and the epsilon we chose are the only ones that will work to prove this adjunction.
That's a very good question. Remember that adjunction is not just functors f and g. It's functors f and g together with this information. So if you were to find another eta and epsilon, you would get a different adjunction. You would not get the same adjunction. However, it can be proved that once you have fixed one of them, then the other one will be uniquely determined. Now, to be honest, I've never in my life proved that once we fix the two functors that we fixed, you won't be able to find another pair, eta and epsilon. My intuition tells me that it shouldn't be possible to find another pair, but I've never sat down and proved that result. So that you might want to try that as an original exercise. But once we require that one of the maps is the one we want, then the other one will be uniquely determined by that one. And that actually will come from a general fact in the general theory of adjunctions, which we still have to, which we'll still look at. I hope that answers your question.
Yes, thank you.
Yeah, just a follow up on that one. If you then happen to find another one, another set of those adjunction, is it expected that it should be related somehow? Can you hear me?
Yeah. No, I'm thinking about your question, Charles. It's a good question.
Okay.
So once again, it depends on what part is fixed and what part is not fixed. For example, if we have f fixed, right? You can actually find many different g's, but all of them will be naturally isomorphic to f, meaning that there will be natural transformations between two different g's, such that their composites are identity natural transformations. And then those isomorphisms between g's will also establish correspondence between the corresponding etas and epsilons. But if once again f and g are fixed and you found completely different pair eta and epsilon to the one we provided, then there is no expectation that there will be any relation between them. because the functors alone have absolutely no information about what the transformation should be. So that's why I emphasize that specifying the transformations is part of being an adjunction. It's part of the data. You can't drop this and say an adjunction is just these 4 things for which those exist. Specifying those is important. In usual examples, these 2 are uniquely determined, but in general, they don't have to be. Does that answer your question, Charles?
Yeah, this classifies the text.
Okay, thank you.
Yeah, thank you. Yeah.
Are there any other questions? Okay. I want to now introduce some terminology related to an adjunction. The F here is called left adjoint. The G is called right adjoint. The eta is called unit of adjunction. The epsilon is called co-unit of adjunction. Okay, so the next thing I want to do is to look at a very simple example. So this example wasn't very simple, right? It was quite complex. By the way, before we look at a very simple example, let me just put this example in context, the one we looked at. So on this side here, instead of vector spaces, we could have had other mathematical structures as well. For example, we could have taken here the category of monoids. Then you can develop the idea of formal, not linear perhaps, but formal combination of elements, which is basically a word of letters. So the functor f will assign to a set the monoid of words where the alphabet is given by that set. The functor backwards will take a monoid and consider the underlying set of the monoid, so the elements of the monoid, and we get an adjunction. And this phenomenon occurs in all sorts of situations, basically with any kind of, almost in any kind of mathematical structures you put here. You always have this nice adjunction with the category of sets where, as Meek referred to earlier, we have this idea of free structure. So F will always be your free structure over your set. And G will be the underlying set of your structure. And these pairs always form adjunctions, and the proof for of that is almost identical to the proof of this situation, where except of formal linear combinations, you will now be working with formal algebraic combinations determined by your algebraic structure. The free and underlying set adjunctions also exist for geometric structures, for example, for topological spaces. In fact, something interesting happens there, which I'm not going to say now, because we still need to develop the theory of adjunctions a bit more before we come to that. So although we did spend a long time on just one example, this example is actually a model example. So many other examples can be produced based on the idea behind this example. And they play an important role in mathematics. You can make things even more advanced. You can replace sets with structures as well. For example, we could have started here with abelian groups. and here still vector spaces. And then what we will be doing is assigning to an abelian group the free vector space over it. But we now no longer take that abelian group to be the basis. We rather, when we take this formal linear combination, we only take formal scalar multiples of vectors in the abelian group, but then the addition is interpreted to be the addition of the abelian group. So we keep part of the structure. So we build the free structure only partially. The part of the structure that already exists on the left side, the abelian group structure, we kind of keep that, and then we only add the structure necessary. We only add it freely by formal combinations, the structure necessary to get that thing. And backwards again is the underlying structure. So for a vector space, we consider the corresponding abelian group of vectors, and again we get an adjunction. And so one can play around with this a lot, and in all such games, you will have arguments proving that you actually have an adjunction, which will be very, very similar to the argument we gave here. So that's why we spent such a long time on this example, because it's an illustration, a model example for many, many other examples of similar kind. But what I want to do now is to show you an example of a completely different kind. And let me take you back to the first lecture when we said that there are two structures, the structure of a monoid and the structure of a preorder, whose kind of conceptual mergers is the notion of a category. So let's now look at the preorder side of things. Let's take a situation where the categories C and D are preorders. And in fact, let's take very simple preorders, the ones that are familiar to us maybe from early childhood, the preorder of natural numbers. Let me call it primitive example of an adjunction. Zero, 1, 2, 3, 4, and so on. These are the arrows in my category. The arrows represent less or equal relations. These are not the only arrows. Any arrow connecting a number to a bigger number will be there, or equal number. These are the arrows that kind of generate the category. Any other arrow will be composites of these, including the empty composites at each object which are defined as identity morphisms. On this side, let's take the continuum of real line. Maybe we just stick with positive. Well, non-negative real numbers. So I'm going to take off the 0 here as well. And we have a very nice insertion of the left category to in the right category, right? So this is our left category, this is our right-hand side category. So here, a morphism we only have from n to some n plus a. This is kind of description of all possible morphisms in the left side category. So, but where of course a needs to be bigger or equal to 0. On this side, the description of morphisms is similar. Morphisms only exist from a real number to some. Maybe I should not use a here. Let me call this s. Morphisms only exist from a real number to a bigger or equal real number. And we have an insertion of the number system. Basically, this is the positive natural number system to the positive real number system. So the 0 is not included there. I'm going to make a hollow point here. 1 is mapped to 1 on the real line. 2 is mapped to 2. 3 is mapped to 3. 4 is mapped to 4, and it goes on like that. So n is mapped to n. And we know quite well that this is not a one-to-one correspondence. Why not? Well, because unfortunately the continuum is not bijective to is not countable, right? It's strictly bigger, so you cannot find not just this specific one, but you can't find any bijection between the natural numbers and the real numbers, or positive natural numbers and positive real numbers. Just like before, we established that we couldn't find an isomorphism between the category of sets and the category of vector spaces. So let's try if we can maybe approximate that. So now we want to go backwards from positive reals to positive integers in a way that we get an adjunction. Any ideas what to do?
If I may take a stab, I'm guessing, I'm going to say the ceiling function.
That's right, yes. Except that if I want the ceiling function, I should have drawn my picture the other way around. Because the ceiling function will always increase. So my etas will now be on the right side. Well, too bad. Let me see if I can, no, it doesn't matter. We will learn to swap directions. We will need to learn to swap directions in category theory a lot later on. So let's maybe get started here.
Before we start, I just have a short, small question. Is it, we could probably also use the closest integer function, except for 0 there, if we're less than 0, then we have to map to 1, and otherwise choose the closest integer function. Would that also work?
I have no idea. Let's see if it will work.
Okay.
So basically the rounding function.
Yes, that's
Yeah.
what I mean.
Let me see. Okay, let's all think together. If that will work. Right. No, it will not work because in some cases you'll be going up, in some cases you'll be going down, and we need to have a natural transformation that's has a universal direction. So
the order needs to be preserved. Oh, the arrows.
the order will be preserved.
Functors, yeah.
But the order will be preserved. But we need to have on the right side we need either eta or epsilon, right? And eta will always needs to increment, and epsilon always needs to decrement, and we can't have a combination of those. So if I were to, let's say, start here, right? If I take this back to 1, then it means that when I apply the two maps, so let's call this f and g, like before. So f goes this way, g goes that way. If I take, let's say, 1.2, I apply g to it, and then I apply f to it. I'm going to get 1, and I have an arrow from 1 to 1.2. So I have the eta situation here, right? But if I start with 0.8, I apply g and I apply f to it, then I get 1 again, and here I have the opposite situation, which is the, so remember that we need to have, so let me go back here. So if we have where did we say? Okay, so it was right here. So we need to have either this natural transformation or that natural transformation on one side. Having this natural transformation means that throughout fg, the values of fg are always less than the values than the original value. And here it means that the values of gf are always more than the original value. Does that clarify, Mick?
Yes, that does. And then my intuition is that we can choose either floor or ceiling.
Yeah.
But then we might need to change on which side the epsilon and which side the eta lies, right?
That's right. But in this case, I don't think we will be able to use either or because with the numbers less than one.
Yeah. So here, if we also had 0 on the left, then we could use floor. And if we have 0 included on the right.
I'm not sure because I think we will still be limiting ourselves. So if we had 0 on the left, where would we map 0? Do we also have 0 here? If we have 0 here as well, then I think you're right. Yeah. No.
Yeah, that was what I intended. So,
yeah.
but in this case, if we don't have 0, then we are restricted to only ceiling.
Yeah.
Okay.
So let me go back now. So I want to have a morphism, a functor G backwards. And we identified already one, but we should be able to prove that that's actually the only one. But before we prove that, let's first establish the one that we identified. So that will be the ceiling function. So G of a real number will be, I think the notation for the ceiling function is this. And on the picture, that means that we are mapping all of these numbers, including 1. We're mapping them back to 1. Then we're mapping all of these numbers, not including 1, but as soon as we pass 1, all of them are going to 2, and so on. If I go back to my definition of adjunction, we need, remember that we need things to be natural transformations. And natural transformations means that some diagrams commute. Like, for example, this was one of the diagrams that should have commuted for eta to be a natural transformation. But when I'm in a pre-order situation, in this diagonal, either I have error or I don't. I have error when this is less than that, and I don't when it's not. So commutativity of diagrams always holds in a pre-order. If B is less than that, and that's less than that, then the composite will be the same morphism as the other composite because we always have at most one morphism from B to there. So all the concepts of category theory where we're asking some composites to be equal to each other, they will automatically hold in a situation where categories become pre-orders. So things will simplify considerably. Not only naturality no longer needs to be shown, we don't even need to show the adjunction identities, these two, because again, these identities were about commutativity of certain diagrams. Let me see if we've got them. So you see, well, I mean, in that case, it's even maybe easier to see. Like, for example, here, if you apply, take this morphism composed with that one, we'll get a morphism from D to D, right? But there's only one morphism from D to T. That's the morphism that exhibits the fact that D is less or equal to D. So of course that composite will equal to our identity. So there's nothing to check except that we do get the family of maps eta and epsilon. So what will eta do? Eta will confirm that if I take a number n, it is indeed less or equal to its own ceiling. In fact, it will turn out to be equal to its ceiling, right? Because ceiling, of course, is the same as g f of n, because f of n is defined as n, right? So n maps to n, as we said before. And what about epsilon? Epsilon of a real number should be something that's so epsilon map should be from fg of r to an arrow to r. It means it must be less or equal to r. But what is fg of r? That's the ceiling of r. And that needs to be, did I confuse things? Yeah, this is the other one. Sorry, this is not going to be epsilon, it's going to be eta. This ceiling is, of course, less than, bigger than r, right? So r will be less or equal to its ceiling, which is fg of r. Therefore, I need to switch my notation here. This is actually f. This one is g. So that's why I said in the beginning that we have drawn it in such a way that things are reversed. And then the one that increases my object going from r to fg of r is the one that's called eta. And epsilon is the one that decreases it. So we have eta here, and we have epsilon here. Then the rest, I think, is correct. So to establish an adjunction, all we need to do is to confirm that n is always less or equal to gf of n, and r is always less or equal to fg of r. And because of this simplification, it's maybe worthwhile to write down what it means to have an adjunction when C and D are preorders. So I'm going to go back to my previous screen. So when C and D are preorders, what is an adjunction? Well, first of all, functors between preorders are just monotone maps. Again, preservation of composition and preservation of identity maps is straightforward by the fact that there's always at most one arrow to enable two objects in a category, in a preorder. So when C and D are preorders, then C and D are preorders, right? So these two things are preorders. F and G are monotone maps. And in this case, eta and epsilon will indeed be unique because they're just the facts that if I take an object C in the preorder C, I apply to it F and then G, that will be something that's bigger than C. So this fact that for every C this is true is what guarantees a unique eta. And the fact that fg of D is less or equal to D for every D is what guarantees existence of unique epsilon. Do you know what such thing is called in order theory?
Is it called a Galois connection?
That's right. It's called the monotone Galois connection. And of course, we have hundreds of examples of, if not thousands, if not infinitely many, examples of Galois connections between preorders. And just to show you another one, I mean, this is one of them, the ceiling function and the inclusion of integers into reals. And to show you another one, okay, by the way, I mean, going back here to the question of whether maybe there was another way to go backwards, as we will learn in the general theory of adjunctions, once we fix, and I already mentioned, once we fix f, g is uniquely determined up to isomorphism. And here, because these are partially ordered sets, so antisymmetry holds, natural isomorphism becomes equality. So if we want our f to be insertion of integers into reals the way we've described, then there's going to be only one way to get the right adjoint to go back, and that is the CD function. So the CD function is the unique right adjoint for the inclusion of integers into reals. And here is another extremely important Galois connection. An extremely important adjunction, where we take function obtained from function f, so an abstract function gives rise to an adjunction as well. So let's say f is a function from set x to set y. Then we have an adjunction where we've got power set of x on one side, power set of y on the other side. We are seeing these as pre-ordered, as ordered sets, with the order being the subset inclusion. And the left adjoint and the right adjoint are given by the direct image mapping. Sorry, this shouldn't be dot there. And by the inverse image mapping. So how can we confirm that this gives an adjunction? Well, first let's describe what these mappings are. So the direct image mapping takes a subset S of X, or in other words, element of the power set, and it maps it to f of S. In other words, the set of all values of f, where the variable comes from the set S. And the inverse image map takes a subset T of Y, and it maps to all x's in X, such that f of X is in T. So that's the inverse image of T under F. Of course, we know these notions very well. We use it a lot in mathematics, at least in set theoretic mathematics. And to confirm that this is an adjunction, all we have to do, according to what we said here, we have to check that f and g are monotone, and we do know that they're monotone, right? If s is less or equal to, if s is a subset of s prime, then of course direct image of s under the function f will be a subset of direct image of s prime under the function f. And similarly, if t is a subset of t prime, then inverse image of t will be a subset of inverse image of t prime. And so we've confirmed that we've got monotone maps, and now we need to confirm that we've got unit and co-unit of adjunction, which is just confirming these inequalities. So if I start with S, I apply direct image map to it, and then I take its inverse image. I need to get something bigger than S. And if I take a subset T, then I take its inverse image under the function, and then take direct image. I need to get something smaller than T. And both of these, of course, trivially hold. We can demonstrate this on a picture. So imagine your function goes this way. So let's say these 4 elements are mapped to there, and there. So these 2 are mapped to the same place, maybe. And maybe there are some other elements that nothing is mapped to there. If you take, let's say this S, right? This is S. You take direct image, you'll get this set here. You take inverse image, now it includes this element as well. So it enlarges. This will be F inverse of F of S. And with the other inequality, with the other inclusion, if you take, let's say this T, you take inverse image, inverse image of T will be just that, and its direct image is this, so it shrinks. Sorry, this is F inverse of T. So you see, and of course, this is not the only set theoretic adjunction, or in other words, Galois collection. There is another one which is historically the first one, the one that Galois considered, that comes from Galois theory. Then there is a general construction which builds an adjunction out of an arbitrary relation between sets. And one example of that is the one that comes from Galois theory. There is another example important in algebraic geometry, which defines algebraic varieties and so on. We will still look at these examples in the future, but I just want to say that adjunctions really are around us everywhere in mathematics. And the notion of Galois connections is just a historical remark. The notion of Galois connection was formulated in 1930s in papers of Orr and Birkhoff. I have to double check this, but I think Orr was first, but it might be that Birkhoff was first. I'm not exactly sure. But that was a time when categories were not invented yet. So invention of categories came in 1945, and general adjunctions were discovered in a PhD thesis of Daniel Kahn, one of the PhD students in the category theory group. And then they were promoted further by MacLean and Eilenberg. And at that time, it was not emphasized that what Daniel Kahn discovered was actually a generalization of what was already present in mathematics in the form of Galois connections. Not that people didn't know it, it was just not emphasized well enough. But on the other hand, it's very important to emphasize that, because Galois connections are historically the first adjunctions we encountered in mathematics, and they also are very important examples of adjunctions. And just like Galois connections are everywhere around us when we deal with more primitive structures like power sets and things like that, adjunctions are everywhere around us where we deal with kind of more complex structures like the categories of sets or other mathematical structures. And that brings us to the end of today's lecture. As you see, there is still a lot to tell about the concept of adjunction. It's not just a single lecture concept. We will do a bit more of the theory of adjunctions in the next lecture. One of the things to do with adjunctions is to look at various different equivalent ways of defining them. For instance, there is this well-known equivalent way of defining a Galois connection, which is not in terms of these inequalities, but rather in terms of equivalence of the fact that C is less or equal to G of D, that being equivalent to F of C being less or equal to D. So this single equivalence, even without requiring F and G to be monotone, turns out to force F and G to be monotone and also force these inequalities. So there is a version of a definition of adjunction that generalizes this equivalence. And that's also very important in understanding how that version fits with mathematical structures. And then there is also another version that defines adjunctions through something called universal properties, which is in some sense the most efficient way of building adjunctions, at least for categories. And so understanding these different equivalent definitions of adjunctions forms part of understanding what adjunctions are, in addition to understanding their examples. And we only kind of climbed up that peak, and now we are almost at the top there. And what we want to do now is to look down from there. And we've been looking a little bit around us in terms of the examples, but there is much more to look before we climb back down from that peak, and then we feel that we've understood the concept of an adjunction.